So we continue with symbolic Python, that's SymPy, by looking at symbolic variables and expressions with SymPy. Like we learned already, SymPy helps us to deal with mathematical problems symbolically instead of getting them in numerical form. So again, uh, symbolic variables and expressions with SymPy is the next second video under the SymPy library of Python. So, and that's of course under the whole playlist on scientific computing. So, SymPy is a Python library for symbolic mathematics. We've seen that already. Unlike numerical computation libraries that use approximations, SymPy keeps mathematical expressions exact. That's like what we call exact or closed form solutions. For example, numerical approximation like square root of 2 is approximately 1.414, but symbolic exact form is root 2. So, SymPy can simplify algebraic expressions, solve equations, differentiate and integrate symbolically, expand and factor polynomials, manipulate trigonometric expressions, and generate LaTeX outputs like we saw in the last video. And to install SymPy, what do? Install SymPy using pip. So you have pip install SymPy. This is the keyword. I did that in the last video. Then pip install SymPy. Okay, I mean, this is the installation now, the process, but because it was already installed, it tells you requirements already satisfied. But if you are using it for the first time, then it does the process and then it gives you what you need to get. Then importing SymPy. So you install SymPy if you didn't have it before, but each time you open a new session and you need to use SymPy, you need to also call it by importing it. More like what in some programming language they call it mounting. You need to mount it to be able to use it. So import SymPy. So you install by using pip install SymPy, and then you import by saying using import SymPy as SP. So and the actual implementation is here import SymPy as SP. So, I mean, this SP is just an alias. It could be SY, it could be SM, whatever you choose. So, so that you won't have to type SymPy each time you need to use it. That's why when you see SP dot something, that is actually referring to this SymPy we have installed. So, numerical versus symbolic computation. So, numerical computation gives approximation, while symbolic computation preserves exact mathematics. So, for a numerical example, now if you import math and you get the result to be math dot square root of 2. So that's going to give you, and you print the results, you get 1.4142, 1356, and so on and so forth. But symbolic example preserves the solution for you the way it is. So it gives you square root of 2 in that proper way. So that nothing is lost. Because no matter how long the decimal place is, you are still cutting off some values basically. So creating symbolic variables now. So like we learned in the other video too, symbolic variables are created using symbols, the symbols function. So you have single symbol. To create single symbol, you have x equals sp dots. Well, I mean, this is just like for single symbols, actually, I think it's better. Let me focus on that. So to create single symbols, you have capital S and but to avoid confusion, sometimes it's better you always use SP dot small symbol. So even if it is one, you don't have to worry yourself. But if you want to create a single symbol, you use capital S symbol. That is single. But for multiple symbols, now you have small s symbols, and then you can create X, Y, Z. Like unlike here where you created just X, you can create multiple here. So, but if you use these symbols for even one, it still works. So you have all of this. Then alternative symbol syntax. So if you want to create A, you could have said sp dot symbol A, B, sp dot symbol B. That's capital S now. And then you can print A plus B if you like, and you get your results like that. So how do you then build symbolic expressions? So for basic expressions, like you want to create symbols X and Y. So you have sp dot symbols X, comma X space Y. Then expression, you have an expression X plus Y. So if you print the expression, you get your X plus Y like that. Then what about fractional expressions? So let the expression, you have already created symbol X, right? So you have X plus 1, 1 in brackets over X minus 1. So if you print the expression, now you have X plus 1 over X minus 1. And that's what you get right there. Then you have trigonometric expression. So expression is SP dot sine X plus SP dot cos Y. So if you print the expression, you get sine X plus cos Y as expected. Then you can also have expression evaluation. So you can evaluate an expression. We did that in the last video also. So in this case, you use the subs keyword to substitute values into symbolic expressions. So you create symbols, sp dot symbols x, then express x squared plus 3x plus 2. Then the result you want is you want to substitute 5 for x here. That's 5 squared plus 3 times 5. That's 25 plus 15, which is 40 plus 2. And that's when we print that result, you get 42 like that. Then For multiple substitutions now, you have x comma y, sp dot symbols x, y. So the expression is x squared plus y. So we want to substitute 3 for x and y for 10. So this is how you do it. So you have 3 squared plus 10, and that's 9 plus 10, which is 19. So for multiple, you have this bracket now. Instead of just saying x comma 5 like we did here, you have expression dot subs, then curly bracket x full colon 3, comma y full colon 10. So it means you're substituting x 3 for x and 10 for y. And the answer total is 19 in that case. Then you have numerical evaluation. So x is sp dot symbols x. So the expression is square root of 2 plus pi. And you know you get square root from SymPy, you get pi also from SymPy. So that's square root of 2 plus pi. And you're evaluating it numerically. And that is the work of this eval. So instead of having just root 2 plus pi, you then have whatever root 2, that's uh 1.41412 blah blah blah, and pi is 3.142 and the rest, and then you end up getting 4.5580621596289 like that. Like if you want higher precision, even the eval can still, so for higher precision now you can tell it how many decimal places you want. So you want to print expression, the same this expression dot eval now. So here it was by default it is how many decimal places? 4, 8, 12, like it's like 14 decimal places. But if you want 50, you can have it. If you want 500, you can have it. Like it just goes very long, right? Just keeps going forever. So if you want just 5 decimal places, you can do that too. 5 decimal places, you can get that. Oh, so of course, okay, for Python, right? For this 5 here, it will make it 4. So if you want 2 decimal places, if you want 1 decimal place, you write 2 here, like that. So you can also want um uh maybe 32 decimal places, you get it too. Yeah, so you can also simplify expressions. SymPy provides several simplification tools. So, like we did this in the last video too. Like you want to simplify x squared minus 1 by x minus 1. You know, x minus 1 cancels x minus 1 and you get x plus 1 left. So just do the symbol, write the expression, and then the simplified form is sp dot simplify the expression, and you print, you get x plus 1. Then you can expand to, so imagine you want to expand this expression x plus 1 raised to power 3. So the expanded form is just sp dot expand expression, and you get this. So imagine if you want this to be x minus 1, so you have minus plus minus like that. You know, what if you want it to be like power 5? So that's also possible. So it gives you that. So you can easily expand like this. So don't forget, one star is multiplication, double star is power. Then you can factor also. You can factor expression like x squared plus 5x plus 6. So the factored expression is sp dot factor the expression, and you print and you get x plus 2 into x plus 3, which if you multiply this here, and you end up getting this, right? Then trigonometric simplifications are possible too. So you have expression like sine squared x plus cos squared x. Of course, you know that's going to be 1, right? But of course, the sine is coming from SymPy. Cos is also coming from SymPy. So if you can then print sp dot simplify. So here, what this is doing is you are simplifying the expression and then you are printing at the same time. So you get 1 because we know sine squared x plus cos squared x is equal to 1. And that can be proven using Pythagoras theorem or other methods. So SymPy supports exact rational arithmetic. So if you have a floating point issue, so you want to print 0 plus 1 plus 0.2, you know, that's like 0.3004. You know, you have some number creeping in here like that. But this SymPy can give you the results in rational form. So rational numbers, now from SymPy you can import rational. So R is now rational 1 comma 3. So that means that is 1 over 3 if you print. Then rational arithmetic then. So if you need a result, the result of rational 1, 3, that's 1 over 3 plus 1 over 6. You know, that's definitely half, and you get that. Okay, what did I not do right here? Did I not run? Okay, I didn't run this on where we imported rational. Okay, and then it works here now easily. Okay, so maybe that one's 1 over 13 plus 1 over 16. What happens there? We get 29 over 208. So easily so. The mathematical constants, we can deal with things like pi. So you want to print pi, so that sp dot pi, you get that. Then Euler's number, you know, that's a 2.718 or something like that. So you get that it's capital E. Infinity to print infinity, just have sp dot zero zero. So it comes like out like zero zero, but it's infinity. Then you have symbol assumptions. So assumptions help SymPy simplify expressions correctly. So positive variables. So you have x is sp dot symbols, and you are making sure that the value x is positive. So it's just a positive is true. So the expression, if you now want to find the square root of x squared, you can easily get that the square root of x squared is x because x is positive, right? Well, without assumptions, right? If there's no assumption that x is positive, then it is better to preserve it as the square root of x squared without necessarily saying the answer is x squared, because you don't know if it is minus x squared or minus x all squared or x all squared. So in that case, we just preserve it better as x squared. So the bulk of the times we do it with assumption that x is positive. So we have integer assumption. So if you have n equals sp dot symbols and n integer true, like you're saying that n is an integer. So because you have said it's an integer, so if you print n dot is integer, it will say true. But if you say false, then it's also automatically, so it will probably negate your claim that is an integer. So you're going to get false here now. So like that, so you can set the stage. So expression trees. So we have expression trees. SymPy expressions are internally stored as trees. So expression arguments, you have x comma y, you create them as symbols, and you have an expression like x plus y squared. So if you print now, you have expression arguments now. So it will give you x and y squared. So these are the arguments of the expression. Then we have that. Then expression type now. So you want to know what kind of type it is. So the expression type now tells you it is an addition thing. So here it just give you the parts, but here the expression argument gives you the parts of the expression, while the expression type tells you if it is an addition or subtraction or whatever you're doing. So then you can also pass expressions from strings. For instance, you want to simplify. So expression equals sp dot simplify x squared plus 2x plus 1. So if you print that, you get x squared plus 2x plus 1. So this one is looking like, this one is not in normal Python format, but by the time you simplify it, it comes into the SymPy format. Simplify, you're making it into SymPy expression. That's what that simplify actually means. Then evaluating past expression. So x is sp dot symbols x, then expression is sp dot simplify x squared plus this, and then you now want to print the expressions with 3 substituted for x, and that's 3 squared plus 2 times 3 plus 1. That's 9 plus 6 plus 1, which is 16 altogether. Okay, now we have symbolic functions. So creating a function, now f is equal to sp dot function f, x is sp dot symbols x, like that. So you create f as a function and create x as a symbol, and then the expression is f of x. So the function is a function of x, and if you print that, now you get f of x like that. Okay, then you can also have built-in functions. So if you have an expression like log x plus x e raised power x, log of x plus exponent of x. So if you print that expression, you get exp of x, exponent of x plus log of x. So these are like built-in functions. You can see you're calling each of them from the SymPy library. Then you have nested functions. So you have expression equals sp dot sine, sine of cos x, right? So you get the sine from sp, you get the cos from sp, but you're taking the sine of that cosine of x. So if you print that, you get sine cos x. Then you have polynomial expressions. So if you create your symbols, x equals, so the only symbol is x here, and you have the polynomial x raised to power 3 minus 6 times x raised to power 2 plus x times 11 times x minus 6. So if you print that, you get this SymPy form of it, x cubed minus 6x squared plus 11x minus 6. That's polynomial expression. So to find the degree of the polynomial, so all you just need to do is just say print sp dot degree. So sp, of course, degree is a function also in SymPy, but you almost find the degree of this polynomial already declared here. And it tells you, of course, the degree is 3 because that's the highest power. So you have 3. Then you can also extract the coefficients. Sometimes we need to use the coefficients of a polynomial. So x cubed, the coefficient is 1, x squared, the coefficient is minus 6, x, the coefficient is 11, and the constant is minus 6. So you then have polynomial coefficient. So you have 1 minus 6, 11, minus 6, like that. Then we can collect like terms. We need that to simplify when we're working in algebra most times. So you have the expression xy plus x minus 3x squared plus 2x squared minus yx minus x. So collected terms now with sp dot collect. That's the keyword here. Collect for the expression, collect like terms in terms of x. So you have xy, there's xy here and there's what minus yx. So you can this those will cancel out. X minus x will cancel out. At the end of the year, minus 3x squared plus 2x squared, that will be minus x squared. So when you run that, you get minus x raised to power 2. Then substitution of sub-expressions now. So sub-expression replacement, you have an expression x squared plus x cubed. So new expression will now be so you need expression the expression dot subs. So you're substituting for x squared and you're substituting y. So anywhere you see x squared, you're going to have y. So finally you have x cubed plus y like that. So instead of x squared, you have y. So maybe for some reason y is x raised to power 2. So you can just have that and you have x cubed plus y. Or you can even go further to say maybe something like okay, yeah, for just the x squared part is taken care of now. So you can also rewrite expressions. So you have an expression like sine x, and you want to rewrite it in other forms. So you can write that as in complex form, like minus I into e raised power ix minus e raised power minus ix all over 2. So you can write sine x in that form. So you can write an algebra, a a trigonometric expression in exponential form. So we also have basic lambdify, converting symbolic expressions to numerical functions. So create your symbol, write the expression x squared plus 1, and then the function, you lambdify the x in the expression. So if you print f of 5, that means this expression x squared plus 1 now, you are substituting 5 for x in the expression. So, and you have, of course, 5 squared plus 1, that's 25 plus 1, which is 26, which you get here. Then you can also numbify with numpy. So you have x symbols. The expression is now signed x. Then f, you lambdify x with the expression using numpy. So numpy is coming here because you're working with an array. So you want to evaluate the function at different points. So the values at which you want to evaluate it. So that the array is now coming from numpy now. So 0, pi over 2, and pi. So you evaluate sine x at 0, you get 0. Evaluate at pi over 2, that's 90 degrees, that you get 1. You evaluate at pi again, this is 1.22 times 10 to the power minus 60, which is as good as 0, right? So this is like 0, 1, 0 in that case. But you have that high level of precision. Then you can have pretty printing. You want to print nicely instead of just having backslashes. So the keyword here is p-print, pretty printing. So x is equal to sp dot symbols x. So you create the symbols. The expression you have is x squared plus 1 all over x plus 1. So sp dot preprint expression will give you like a near proper form of printing. That's x squared plus 1 over x plus 1. Otherwise, if you did not do this, it should have just been print expression and it would just bring it in terms of backslashes, x squared plus 1 over x plus 1. Okay, so pretty printing makes it as close as possible to how you would write it in a paper, in a book. So you then have a better notebook printing, sp.init underscore printing. So like that. So we have that. Then here, LaTeX outputs now. You want to integrate sine x with respect to x, and the LaTeX code is sp.latex. So what this does for you, it gives you your result in LaTeX. So you can just copy it into a LaTeX document and then get your results. One thing you can do with this is, so this now you can copy it and say you have a cell, if you have a cell here, just put it within dollar signs and it returns it in that pretty LaTeX format. So this is very good if you want to copy into a LaTeX document and just have it run in LaTeX. Then common mistakes. You can have common mistakes. You can have incorrect use of math.sign. So so if you import math, x is sp.symbols. So you're importing math and then you're using sp.symbols. That they don't work together. So if you're bringing sign from if you're bringing sign from SP, feel free to do that. You can bring sign from math, but they are different in this case. So just know you're using SymPy here. Then correct use of sp.sign would be, so you have your expression equals sp.sign of x. Of course, that way you would have imported SymPy already, so you can call sign from it. But the fact that you can call sign from math does not mean you should use it here for symbol, because sp you can also call sign from SymPy, right? Then you can have mixing floats. So imagine you have expression 1, 0.5x, and then expression 2, you now have 1 over 2 times x. So if you print, you can print expression 1, and that's 0.5x, and expression 2 is 1 over 2. So the two expressions are basically they are technically the same, right? But if you want to have them in fractions, put everything together in fraction. If you want to have them in float like 0.5, have them in that format. So don't mix things up as much as you can. Then mini project, symbolic quadratic analyzer. So create a polynomial, say create the symbol x, then create your polynomial x squared plus 5x plus 6, then print that's x squared plus 5x plus 6. So you can factor that. So to factor it, if you have SP the factor of the expression and you print and you get x, okay, this, I run this first, then we come here. And then to factor, you have x squared, x plus 2 into x plus 3. Then if you want to solve the same expression now, so the solutions will be sp dot solve expression with respect to x, and you get minus 3 and minus 2 as expected. Then you can differentiate the same expression. Of course, if you differentiate x squared plus 5x plus 6, you get 2x plus 5, which you have right here. And then you can plot the function too. So it's more like the same expression, you're doing different things with it. So that's one beauty of this. So you can do as many operations as you want with it. So that same function I can plot. So in this case now you're bringing NumPy, you're bringing matplotlib for visualization. Then you can lambdify. So X expression using NumPy. So then you are evaluating at minus 10, 10 in 400 divisions. Then you get the values and then you do your plot, your quadratic plot, which you have right here appearing this way. So in summary, in this lesson, you learned symbolic mathematics, creating symbolic variables, building symbolic expressions, simplifying expressions, exact arithmetic, symbol assumptions, expression manipulation, polynomial operations, 3D printing, numerical conversion using lambdify. So these concepts form the foundation of symbolic computation with SymPy. So you have some problems to practice with. So let's show 1 to 3 for now. Okay, let me, even if it is two, it's not a problem. Create symbolic variables x and y. Of course, you already know that's just going to be x comma y equals sp dot symbols, then open bracket in quotation dash dash, you have x space y. Then construct the expression x plus y. So you just say expression equals x plus y, and you can print expression and you get this x plus y. Then you can create this polynomial in like manner too. Just don't forget that x squared is x star star 2 plus 3x. 3x is 3 star x plus 2. So, and you can create that as expression and print. So same for problem 3. Problem 4, you can factor. Problem 3, you can expand, right? You already know you create the symbol, create the expression, and use the expand keyword. Then factor, problem 4, follows the same process except that you want to factor this time around. And of course, that will clearly be x minus 3, x plus 3. Then problem 5, you want to simplify. We've done this a lot, and you get your answer to be x plus 1. Then you can substitute 4 for x in this expression, where you get 16 plus 20. That is 36 plus 1, which is 37. Then problem 7, evaluate numerically root 2 plus pi to 20 decimal places. Of course, you're going to use eval here. Eval, you want to get the exact value instead of keeping it in this form. Then problem 8, create the trigonometric expression sin squared x plus cos squared x, then simplify it because you know the answer is going to be 1. Then problem 9, create symbolic variables ABC, build the expression a squared plus b squared plus c squared. Of course, you create the symbol a comma b comma c equals sp dot symbols, open bracket, apostrophe a space b space c apostrophe close bracket. Then expression will now be a star star 2 plus b star star 2 plus c star star 2. And then you can print the expression and you get it. Then problem 10, you want to expand x plus y raised to power 4. That's possible. Factor x squared plus 7x plus 12. That's going to be x plus 3, x plus 4, most likely. Find the degree of the polynomial. Of course, we know the degree is 4, but you want to use it the SymPy way to do it. Then problems 13 and 14. Extract the coefficients of x cubed minus 6x squared plus 11x minus 6. We did that before. You want to do the same. So we have problem 14, create the expression sin x plus cos x. We write it using exponential form. You can do that too. Then problem 15 and 16, create a positive symbolic variable x. Simplify square root of x squared. Convert the string x squared plus 2x plus 1 into a SymPy expression. You can do that. So yeah, that's where you simplify. Then you have okay, create a symbolic function f of x. We did that before, so you can also try your hands to be sure you understand. Then you want to substitute x equals 2 and y equals 5 into x squared plus 5y. We've done that before, so just adapt. Then we have finally problems 19 and 20. Create a numerical function using lambdify for x squared plus 1, evaluate it at x equals 10. Then problem 20, create and simplify the expression x squared minus y squared all over x minus y. With this, we come to the end of this interesting video about symbolic variables and expressions in with SymPy. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, the question is, what exactly are you waiting for? Why not go ahead right now and uh, subscribe? Hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can actually become a member of the channel by clicking on join, and that gives you special privileges like like getting to see some videos first before others, or seeing some videos exclusively. All right. You can see some videos exclusively as a member of the channel. You can also request for PDF copies of the notes I use for teaching. Then we can also hang out to discuss whatever interests you on my channel, either virtually or physically if you're in the same geographical location. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing math right, keep doing Python right, keep doing data right. Bye.